Hello and welcome to my video lesson 3.1 on magnetism. So magnetism is very similar to charges. In charges with electric charges we have like charges repelling and opposite charges attracting. So similar to that, with magnets, like poles repel, so north and north repel, and opposites attract, so north and south attract. So when we draw, so that's important to know about, but moving on, when we draw magnetic fields, we draw the arrows as if we placed a normal compass in that location. What way would the north arrow point? Another way to ask that is, how would a north magnet be pulled if you put it into that location? And obviously you can't just have a north magnet, it has to have a south pole on that magnet as well, but we just kind of imagine a north position in that spot. So with that in mind, how would a magnet be pulled? A compass be pulled if it's next to this magnet? Well, it would be pulled away from the North Pole and towards the South Pole. So we're going to have these looping curves coming around from north to south, over and over again. So a compass would be pulling away. Okay, what's cool, if we're trying to do a more uniform field, we can look between a North Pole magnet and a South Pole magnet, and between there it's almost more uniform. Okay, but you can still see the directionality to it is always north to south. Okay, there are different types of materials. We have permanent magnets. Neodymium is the most common, but there's all sorts that are listed there. They hold their magnetism for a long time, like years. Temporary magnets, which only stay magnetized for a short time, like hours. You can kind of rub a magnet against an iron nail, for example, and just get it to be magnetized for a little bit. Okay, and then there's non-magnetic materials, so like rocks, obviously, but also copper cannot be magnetized. You can rub it with a magnet, it won't get magnetized, which is important for later when we're talking about Lenz's law we'll look at later. Okay, there are two questions we're going to take a look at today. Since opposites attract, the north end of a compass points at a south pole of a bar magnet. That is pretty straightforward, right? If this is our bar magnet and we have a compass down here, the needle will point at the south pole. Okay, so normally we label the compass like this: north, east, south, west. Never eat soggy wieners. And you point it towards the north pole. Okay, and because there's the magnet there, it's always going to be attracted to this south pole here. Now, with that in mind, what is the magnetic polarity of the geographic North Pole? Well, actually, the geographic North Pole is actually south, because if you're in Canada, the north end of the compass points north. Well, to the North Pole, right? North Pole's up there, but it's actually south magnetically. Because, again, if you're in Europe, it points north. If you're in South Africa or in Brazil, it always points towards the north. So the magnetic field lines are always pointing towards the north, which means it's actually south magnetically. And that also means that the South Pole is north magnetically. So, with that in mind, what do the field lines look like? Well, it always goes from the South Pole to the North Pole. So we're going to have these lines looking kind of like this. And it's not always clear, but the lines are always going in kind of this direction. So the North Pole is actually magnetically south, while the South Pole is actually magnetically north. All right, that's interesting. Let's take a look at some field lines here and see if we can figure out the North and South Pole of the horseshoe magnet now. So we already know the field lines on this question. So if a north pole was in this field, it would get attracted this way. Well, that means this has to be south, which means it's being repelled from the north side. So it's north and south from left to right. All right, I hope this video helped you better understand magnetism and especially the field lines within there. Hope it helped. Good luck.